Okay, Bismillah ar-Rahman ar-Rahim. We have reached the last problem in the problem set, which is problem 5.3. For this problem, we are given the molar flow rate, the absolute pressure, and the temperature, and we need to determine the volumetric flow rate of ethane using the different approaches here. So let's begin with the ideal gas law. As you know, the ideal gas law is given as PV equals nRT. You can use the volumetric flow rates and the molar flow rates as well for the ideal gas law. And by substituting the givens, you will get a value of 15.42 liters per hour of ethane. Don't forget to convert the temperature to Kelvin and use the appropriate value for R. Now, for part B, we need to use the truncated virial equation. For the truncated virial equation, you will need to gather from the tabulated data, you will need to gather the critical temperature of ethane, which is 305.4 Kelvin, the critical pressure of ethane, which is equivalent to 48.2 atmospheric. You will also need to find the eccentric value, 0.099. Again, all of these values are given in tables in the textbook. And to calculate T reduced, which is basically T of the system over the critical temperature of ethane. So from the question, we have given that T of the system is 313.15 Kelvin after converting from Celsius to Kelvin, of course. And the critical pressure, as we found from the table, we divide them, we get the T reduced. Okay, now we are ready to use the truncated virial equation, which is this one here. So to find the truncated virial equation, we have P, we have R and T. We need to calculate the virial coefficient B. To calculate the virial coefficient B, we will have to go through multiple steps. So the equation for the virial coefficient B is this. So basically, we first need to find B0 and B1 and then substitute them in this equation to get the virial coefficient B. So we have the equation for B0 is given by this. You will substitute T reduced in here to find to arrive to this value of B0. And then for B1, you will use this equation, and then you will also use the reduced temperature, and you will arrive to this value. After you substitute these values of B0 and B1 along with the critical temperature and critical pressure and the eccentric value, you will arrive to a value of B that is equal to negative 0.168. So it's like a pyramid. You work your way like that from B1 and B0, then B, and then you substitute B back into the virial equation. So when you substitute B back in the virial equation along with the givens which are P and T and R, so you will substitute it, and in the calculator, instead of the molar volume, I just put X as an unknown, and then I pressed on shift solve to get X, which is basically the molar volume, which is the molar flow rate over the volume flow rate over the molar flow rate, and then you just multiply the value of the molar volume by the molar flow rate to arrive to the volumetric flow rate, which is 13.025 liters per hour of ethane. Now, to use the compressibility chart, we have this equation. Okay, and what we need to do, so we know P, we know the molar flow rate, we know R, and we know T. We need to find the Z. So basically, we will use the charts, the compressibility chart, to find the value of the Z. So for the compressibility chart, when you are given a compressibility chart, you have values of reduced pressure and you need to map these values of reduced pressure to the values of reduced temperature to arrive to the appropriate value of Z. So here we already calculated the reduced temperature from the last part, which was equivalent to 1.025. And to calculate the reduced pressure, we will just need the pressure of the system, which is already given as 20 atm, and the critical pressure, which we collected from the tabulated data. And once you divide them, you will arrive at a value of 0.414. So keep this in mind, because now we will go to the chart. So here in our lecture notes, you will find the charts. So you might think that they are different, but they are all. So you might think that this chart is different from this chart, and it's different from this chart, but it's not different. It's all an expansion of this chart. So basically, the charts below are just zoomed in, and you have this axis a bit rescaled so that it's appropriate to use for low pressure cases and medium pressure cases and high pressure cases, but they are all the same chart, okay? They are all an expansion from the same chart, I'm sorry. Okay. So now I will use this expansion of the chart. So as we said, our value of PR was around 0.414. So here you will see where that is, and it is right here. And then we found that T reduced to be around 1.025. So we will go. So here I will go in between, because I have a T reduced of around 1.025, and we will see that this maps us to a value of the compressibility factor that is almost 0.86. This is an estimation. So here we have that Z is around 0.86. Then you will just again substitute all the givens and the Z to solve for the volumetric flow rate. And you will get a value of 13.26 liters per hour. Okay, now to use the cubic equations of state, you can use any of them. I used the van der Waals equation. So basically, this is the van der Waals equation, and you need to find A, you need to calculate A and B. We have R, we have P, we have T. We need to find A and B. So A is basically this equation here. We have R, we already have from the tabulated data the critical temperature and critical pressure. You just substitute, and then you will arrive to a value of 5.49 for A. And for B, the same thing. You have this equation for B. You will just substitute in the value for the critical temperature and the critical pressure, and you will arrive to a value of 0.064 for B. And then you will substitute the givens and the values that you just calculated of A and B. And as we did before, for the molar volume, I just substituted X here because I wanted to use the calculator. And then you just press shift and solve in the calculator to find the value of the molar volume. And once you find the value of the molar volume, it's easy to find the volumetric flow rate by multiplying the value of the molar volume by the molar flow rate, and then you will get a volumetric flow rate of 13.42 liters per hour of ethane. Now, for the last part, we need to calculate the percent deviation from the ideal value. So here, so we would use the values obtained from part B in the Virial equation, part C, we used the compressibility chart, and part D, we used the van der Waals equation. So we will put each obtained value, subtract from it the ideal value from part A, then we will just find the percentage of each. I took the absolute value, wait, not negative, like the negative just signifies that the obtained value negatively deviates from or is lower than the ideal value. So basically this was the last problem. If you have any questions, please don't hesitate to ask in the comments, and thank you.